Hello, Math Studies students. Welcome to another online lesson. Today we are going to talk about the probability of independent and dependent events. We will know we're successful when we can solve IB level problems, such as those in the homework involving independent and dependent events. This will be one of our first lessons that involves formulas. So you'll probably want to copy these down. Also, you'll want to take a look at your formula packet and find these formulas in there. Or I guess first and foremost, identify if they are in there, and then do they look the same and where are they located. Independent events are those where the occurrence of one event does not affect the occurrence of the other. Occurrence is like the happening, or whether or not it occurs. So if they're independent events, they don't affect each other, and all you have to do is take the probability of one times the probability of the other. Multiplication. Multiply the two probabilities together, and that will get you your combined probability of those independent events. And you can extend this rule for any number of independent events. So if I've got one independent event, that would be an example of like flipping a coin, and then maybe rolling a die. What I do with the coin does not affect what happens with the die, and so they would be independent events and they can be multiplied. And then maybe the weather. The weather is not affected by my die or my coin. Just multiply them together, and that can continue on and on and on. So let's try that out. Example 1. As I just mentioned, classic example, a coin and a die are tossed simultaneously. Without using a diagram, determine the probability of the following. A head, that would be on the coin, and a 3. So two things happening. We're getting a head and we're getting a 3. First, we need to ask ourselves, what is the probability of getting a head on a coin? And again, this is theoretical probability. So we think of what are all the different outcomes of a coin. That's 2, heads and tails. And of those, we only want a head. So our desired outcome is 1 out of the 2 possible, so a probability of 1/2. Then to get a 3 on the die, remember, we're not looking for 3 different outcomes. We're just looking for 1. It's a 3. You can get a 1, a 2, a 3, 4, 5, or a 6. We just want the 3. That's 1 out of 6 possible outcomes. And then all we're going to do is multiply those. Now, of course, you can reach for a calculator and do that multiplication problem with the calculator. But there's something I often say in class, which is multiplying fractions is easy. The reason I say that is you don't need to have a common denominator. You don't need to do a reciprocal or anything like that. You just go straight across and multiply. So we multiply the numerator, which is 1 times 1, which gives us 1. And then we multiply the denominator, 2 times 6, which is 12. And so our probability is 1 out of 12. Referring back to last lesson, the likelihood of this occurring is less likely. In fact, it's very close to 0, and so it's not a very good chance of that happening at all. The second one asks for a head and an even number. So a head, once again, that's 1 out of 2. An even number, well, half of the numbers on a die are even, 2, 4, and 6. So that's 3 out of 6, or you could reduce that to 1/2 right away. We multiply straight across, and we get 3 out of 12. Now you can leave your answer that way. You can turn it to a decimal. You can reduce it. If we reduce it, we see that both the numerator and the denominator are divisible by 3, which becomes 1/4. So 1 out of every 4 trials should theoretically end up with a head and an even number. Still less likely to occur than half the time. Finally, a tail, which is still only 1 out of the 2 possibilities on a coin, and not a 6. That would be a complement. So if we know there's only 1 6 on there, that means all the remaining options are not a 6, which would be 5 out of 6. And then again, we're going to multiply because they're independent. So 1 times 5 gives us 5, and 2 times 6 gives us 12. So 5/12, it doesn't reduce. It's almost half, just not quite. So almost half the time we would expect to get a tail and not a 6. This time we're going to look at a problem with some percentages for our probabilities. Gabe attends school 95% of the time. Michelle attends school 85% of the time. Find the probability of the following. Michelle attends, but Gabe does not. So we're going to have to use some complements here. Again, if you think you can do this on your own, go ahead and pause the video. But for part A, we're going to start off with the first of our independent events. Again, we're assuming they're not related or carpool or something like that, so they're independent. And Michelle has not as good of attendance as Gabe. She attends 85% of the time, or I already went to a decimal so I can put that in a calculator if need be. So I've got 0.85 is the probability that Michelle attends, but Gabe does not attend. And so that's a complement. Whenever you're trying to find out the not, we looked at our formula last class, you take 1 minus the probability that she will attend, and that leaves the complement of 0.05. So we're going to take 0.85 times 0.05, 5% of the time Gabe does not attend. We're going to throw that into a calculator, and we end up with 0.0425. That's an exact figure. You can press math, enter, enter, and turn that back into a fraction. But I didn't round, and it's 3 significant figures anyway. Maybe best would be to turn that into a percent, since the original problem had percents. So I move the decimal place over twice, and I'm left with 4.25%. Moving on to part B. Gabe attends, but Michelle does not. So this time we take Gabe's 95%, do our complement for Michelle. Again, 1 minus 85%, or 100% minus 85% leaves us with 15%, or 0.15. We go ahead and multiply those, and we end up with 0.1425, also known as 14.25%. Not very likely to occur, but more likely than the last one. Over 3 times is likely. Part C, both students attend. This is the most straightforward. We take their 0.85 times the 0.95, and we get 0.8075, also known as just over 80%, 80.75. You'll notice I didn't round to 3 significant figures because it's an exact value. No need to round. So 80% of the time, they're both here, just over. And last but not least, neither student attends. So all we do is take our 2 complements, 0.05, which is the probability that Gabe does not attend, times 0.15, which is the probability that Michelle doesn't attend, and we end up with 0.0075, also known as 0.75%. So less than 1% of the time, neither student is there. All right, this takes us to our second part of our learning intentions, talking about dependent events. Dependent events are events where the occurrence of one event does affect the occurrence of the other event. I'll do sort of an illustration of this a little bit next class, but we'll probably look at one example still here on this video. We're still going to multiply if they're dependent events, but you have to do an extra step. You have to figure out what is the probability of the second thing occurring, knowing that the first event has already happened. An example of that would be picking teams. If I knew there were, let's say, 20 students on a team, and or in a class, and let's say that 11 of them were males. We had 2 captains picking. Captain A picked first. What's the probability that Captain A is going to pick a male student? If he picks it totally at random, we'd say, okay, well, the total of students is 20, and the desired male outcome would be 11 out of 20. So 11 out of 20 would be the probability of picking a male. However, now let's say Captain B gets to pick. What's his probability of picking a male student? And again, if it was totally random, he would put his total on the bottom. But remember, somebody's already been picked. The first team already picked a male. And so now there's only 19 students left. And since the first one got a male, 11 out of 20, what's the probability now that the second one will also be a male? Well, there's only 10 males left. Why 10? Because the first one already picked a male. So there is 1 less student, and there is 1 less male. That would be the idea. Now, if they went back to the other one, what's the probability of the original captain picking another male? Well, now we're down to 18 total students because 2 have already been picked. First one was picked here, second one was picked there, so we're short 2 students, and we're short 2 male students. So now it would be 9 out of 18, and so on and so forth. And then we would just multiply those together. So what's the probability that the first 3 picks were all males? We would just multiply these 3 fractions together, and that would be the idea of dependent events. So we'll work through this one together. I think I have one other example that maybe we'll take a look at in class when we discuss this a little bit further. Box contains 4 red, 3 blue, and 1 white marble. 2 marbles are selected at random without replacement. Find the probability that both are red, both are blue. First is white, second is blue, neither is white, both are white. So without replacement, replacement means to put back, or replace is the root of that word. And so we're not going to put back. So we take 1 marble out, and then we reach in for a second one. So first we're going to start with the idea that both of them are red. Well, we have to find our total. So we're going to add all these up. 4 plus 3 plus 1 gives us 8. And so to start with, there were 4 red marbles. That's our desired outcome out of a total of 8. Once we take our first marble, we no longer have 8 marbles left. There's only 7 left. And assuming we got the red one, which is what we're finding the prediction for, or the probability of, there's only 3 red left. So in order to get 2 red, the first one had to be red, and the second one had to be red, but there's 1 less red and 1 less total. So then we multiply straight across, and we get 12 over 56, which does reduce, but I'm not worried about that right now. Second, the probability that both are blue. So we start off, there's still 8 marbles. We're going to start over again. And so we've got 3 blue out of a total of 8. But once we pull out that first marble, there's 1 less blue marble. So there's only 2 blue marbles now, and there's only 7 total marbles because we took out 1 blue already. We multiply straight across, we get 6 out of 56. Next, we go to the part C. The first one is white, and the second one is blue. So we start off. How many white ones were there? Well, we had 1 white. So 1 out of the 8 marbles were white. And the second one is blue. Now remember, we took a white marble out, so there's only going to be 7 total. But we haven't taken any blues out yet, so we should still have all 3. Because remember, our first pick was a white one, so we should still have all of our blue ones left, all 3 of them. But our total has shifted down to 7. Now we multiply straight across. We have 3 over 56. Find the probability that neither is white. Well, there was 1 white marble, so that means there were 7 marbles that were not. Then take all of them, take away the one that we're not talking about, which is the white, and we're left with 7. And then if I take away one of those 7 marbles, I'm left with 6 non-white marbles, and a total of 7 marbles left. Multiply straight across, we get 42 over 56. And last but not least, part E, both are white. We end up with 1 out of the 8 that was white. Once we take away that 1 marble, there are 0 white ones left, and a total of 7 marbles left. If we multiply straight across, anything times 0 gives us 0. 0 divided by 56, 0 divided by anything gives us 0. Remember, we can't divide by 0, but we can divide 0 into 56 groups. Every group would contain nothing. So there's no chance of getting 2 white marbles. Why wouldn't there be a chance of getting 2 white marbles? Because there was only 1 white marble to begin with. So there's no way you can pull out 2. So it makes real world sense as well. And I think I'm going to end with that example. There is one other example here if you want to take a look at that. But I think we'll discuss this a little bit more in class. From the book, we've got a handful of problems that I recommend taking a look at. On page 273, problems 1, 3, and 6. And then on page 274 to 275, problems 1 to 3. We're going to take a test on basic or experimental probability next class. So that would be like the handouts that we got on our very first lesson, dealing with given data and creating probability based on that.